Container with most water. Imagine you're given an array that secretly encodes the largest container you can fill. Can you find it? Container with most water is a classic Pattern Mastery 100 problem, beloved by Phong interviewers because it tests for true insight into two-pointer patterns. Nearly half of all candidates stick to brute force and miss the elegant ON trick. If you can master this problem, you'll have a powerful template for dozens of similar questions. Let's crack it open together. Let's break down the problem. You're given an array of heights. Each height represents a vertical line on the x-axis. Pick any two lines. Together with the x-axis, they form a container. The goal? Find the pair that holds the most water. Area is calculated by the distance between lines times the shorter line's height. Let's assess our options. Brute force would check all ON squared pairs, much too slow for large arrays. The real trick? Notice that the only way to increase area is to move from the widest container to a narrower one, but hopefully with a taller line. That means we can use 2 pointers, starting at each end of the array, always moving the pointer pointing to the shorter line inward. This way, we never miss the optimal solution, and we do it in linear time. Here's the structure of our solution. Set 2 pointers, left at the start and right at the end of the array. While left is less than right, do the following. Calculate the area using this formula. The minimum of height at left and height at right, multiplied by the distance between them, which is right minus left. If this area is greater than the current maximum area, update the maximum. Then, move the pointer at the shorter line inward. Either increase left by 1, or decrease right by 1. Finally, return the maximum area found. Now let's try to implement it using solution 1. We're defining a function called maxArea that takes an array height. We create a variable maxArea and set it to 0. This will store the biggest container area we find. We store the length of the array in n. Now we use 2 nested loops to try every possible pair of lines. The outer loop picks the left line at index I. The inner loop picks the right line at index j, starting from I plus 1. So we don't repeat pairs. For each pair, the container height is the smaller of the 2 lines. So we take math.minHeight, ij. The container width is the distance between them, which is j minus I. So the area is math.minHeight, I, height j, times j minus I. If this area is bigger than our current max area, we update max area. After checking all pairs, we return max area. Time complexity is O of n squared, because we try every pair. Space complexity is O of 1, because we only use a few variables. Let's verify solution 1 for container with most water. Input is height equals 1, 8, 6, 2, 5, 4, 8, 3, 7. We check every pair of indices, and compute the area each time. The best pair ends up being index 1 with height 8, and index 8 with height 7. The height of the container is the smaller value, which is 7. The width is 8 minus 1, which is 7, so the area is 7 times 7, which is 49. The output is 49, and the expected is 49. They match, so solution 1 is correct for this test case. Now let's try to implement it using solution 2. We're defining a function called maxArea that takes an array height. We create a variable maxArea and set it to 0. This will store the biggest container area we find. We set 2 pointers, L at the start of the array, and R at the end. Now we run a loop while L is less than R. Inside the loop, we compute the container height H as the smaller of height L and height R. We compute the width as R minus L. So the area is H times R minus L. If this area is bigger than max area, we update max area. Now we decide which pointer to move. If height L is smaller than height R, the left side is limiting the height, so we move L to the right to try a taller line. Otherwise, the right side is limiting or equal, so we move R to the left. When the loop ends, we return max area. Time complexity is O of n, because each pointer only moves inward, and each index is visited at most once. Space complexity is O of 1, because we only use a few variables. Let's verify solution 2 for container with most water. Input is height equals 1, 1. We start with L equals 0, and R equals 1. The height is the minimum of 1 and 1, which is 1. The width is 1 minus 0, which is 1. So the area is 1 times 1, which is 1. We update max area to 1. Since the heights are equal, we move R left. So R becomes 0. Now L is not less than R. So we stop. We return 1. The output is 1, and the expected is 1. They match, so solution 2 is correct for this test case. Let's recap container with most water. This one is all about turning a geometric idea into a smart search strategy instead of checking every possible pair. You're given an array of heights, and you need to pick 2 lines that form a container with the x-axis. The amount of water the container holds depends on two things: the distance between the lines and the height of the shorter line. So even if one side is very tall, the shorter side is what limits the area. A brute force solution would compare every pair of lines, but that quickly becomes O(n squared). The key insight is that you don't need to test everything if you move strategically. Starting with the widest container and shrinking inward only where there's a chance to increase the limiting height leads to a much faster approach using 2 pointers. We place one pointer at the start and one at the end. At each step, we compute the area and update the best results seen so far. Then we move the pointer at the shorter line inward, because moving the taller side can't improve the limiting height, and it also reduces the width. We keep going until the pointers meet. We implemented this successfully on LeetCode without errors by sweeping inward from both sides, calculating areas as we go, and always choosing the pointer move that still leaves room for improvement. The logic stays simple, but it systematically finds the maximum without wasted comparisons. LeetCode test cases confirmed the approach. For 1, 8, 6, 2, 5, 4, 8, 3, 7, it correctly identified the best container formed by heights 8 and 7, giving a maximum area of 49. And for a small case like 1, 1, it correctly returned 1, matching the expected results. The takeaway is that efficiency often comes from understanding what truly controls the outcome. Once you recognize that the shorter height is the bottleneck, the 2-pointer strategy becomes a natural way to solve the problem in linear time with confidence.